Welcome to part B of our lecture. In part B, we will go through section 9.5 and 9.6, where in 9.5, we will see how the quantum mechanical model we covered in chapter 8, how it is used in explaining the trend in chemical properties of element on the periodic table. And lastly, in section 9.6, we look at the periodic trend on the periodic table, that is the size of the atom's effective nuclear charge. In 9.5, the observation we made in chapter 8 on quantum mechanical model of an atom on quantum numbers. In 9.5, the quantum mechanical model of an atom explains the chemical reactivity of elements, in the sense that elements in the same column, which is the same group, such as in group 8A, they react the same way, or they are inert. It means they do not react because they have valence shell completely filled with electrons. You look at how many electrons there are in the outermost shell for group 8, except for helium, they have 8 electrons. For alkali metals, which is group 1, they have 1 valence electron in the outermost shell, which is used in chemical reaction. All group 1 react the same way. Group 2A alkali earth metals, they react the same way. Group 7A and other main group elements follow this trend. And this has to do with the quantum mechanical model of an atom, which is used in 9.5 to explain the chemical reactivity of these elements. Quantum mechanical model explains this because the number of valence electrons, which are electrons in the outermost shell, and the type of orbitals they occupy also on the periodic table. Elements with the electron configuration closer to noble cars are the most reactive. Remember, noble cars are group 8, group 1, which is the most reactive, because when they lose the outermost shell electron, which is the valence shell electron, they remain with 8 electrons in their valence shell. We'll see in group 8 noble gases, except for helium, they have 8 electrons. 2 plus 6 is 8. Except for helium, they have 8 electrons. We call these inert gases because they are non-reactive. The reason why they don't react is because noble gases have electron configuration with 8 electrons on the valence shell. Alkali metals, which is group 1, remember how we name groups, group 1A on the main group, group 1 or 1A. These are alkali metals. They are very reactive because of 1 electron in the outermost shell is forced to form a cation. So they form a cation with a charge of +1, e.g., all right, sodium, which is a neutral atom, will lose 1 electron in the outermost shell to form a cation. This is 1 or loss of 1 electron. It follows the same thing for all the rest of group 1 metals except for hydrogen. They lose 1 electron, remaining with 8 electrons in the outermost shell, which is the same as group 8. Using an illustration here, this is sodium. See sodium atomic number 11. 2 electrons in the outermost, in the innermost shell. These are electrons. These are electrons. 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And there is one valence electrons. This is valence electron, which for sodium cation, which has a positive charge of 1, will have 8. Now you see where we have 8 electron in the outermost shell. That's what is meant by that. In the reaction, alkali metals tend to lose 1 electron. This is the 1 electron being referred to. This is the valence electron in sodium. Likewise for all other elements in group 1, potassium, rubidium, cesium, francium, and cesium. You can see here they will form cation with a charge of +1. I charge of +1 simply because we have 11 protons for a neutron, sodium, and 11 electrons. But when it is ion or cation, there is we have 11 protons and then electrons, 11 protons and then electrons, forming a charge of +1. For group 7 halogens, since it's close to 8, if you look at group 1, 2A, 3A, 4A, 5A, 6A, 7A, and 8A here, to achieve group 8 electron configuration halogens, which are group 7. This is where we have halogens. They gain 1 electron to be like group 8. 5 plus 2 is 7. All group 7 have 7 valence electron, and they gain 1 electron to be like group 8. Let's see fluorine, for example, which is number 9. In the innermost shell, we have 2 electrons. We have 7 electrons. 7 electrons. So we count 9. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 electrons. We have 9 electrons. To be like group 8, this will gain 1 electron. So if I have fluorine, not iron, but fluorine plus gaining 1 electron will be fluoride with a negative, and this will have 8 valence electrons. So these are the 2, then the 7 here. 1, 2, 3, 4, 5, 6, 7, and then the additional extra electron here using the red is because of the negative. So all group 7 will have an overall charge of -1. So we have the chloride, we have the bromide, extra electron, we have iodide, there is astatine 80. This has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We say they are isoelectronic. It's like isoelectronic means same electron. So here, all these we see here, we say they are so electronic to fluorine. These are right here, fluorine right here. This alone is isoelectronic to neon. Fluorine is isoelectronic to neon. Sodium positive is isoelectronic to neon, means they have the same electron. So reaction of non-metals, they gain extra electron to be like group 8, group 8. To predict the ionic charge, of course, to write the electron configuration of the ionic charge, you include the negative charge. Those form overall charge like group 8 electron configuration of e.g., for example, here, fluoride electron configuration will be 1s2, 2s2, 2p6, and 3. This is 1s2, 2s2, 2p6. So we have here a electron, 3s, 1s2, 2s2, 2p6. This gives you 10. So we don't need these extra. These are 10 electrons. We say these isoelectronic to neon, Me, isoelectronic to neon. This is group 7 for all group 7A or 17. For cations, that is calcium ion. This is 1s2, 2s2, this is 4, 2p6, 10, 3s2, 12, 3p6, 18. But since we have lost the 2 electrons in the 4s, we remain with 18, 3s2. So here these are 18 electrons, which is isoelectronic to argon. If you look on the periodic table, argon is number 18. This is isoelectronic to argon. We say isoelectronic to argon on the periodic table. They gain on for group 6A, they gain 2 electrons to be like group 8 as well. These are the charges. You can look at the group 1, group 2, group 3A, predominantly aluminum will form positive 3, 5A, negative 2, negative 3. You don't see negative down here because you are in the metal territory. Metal tend to lose valence electron to form cations. Non-metals gain electrons to form anion. We saw this earlier on group 8. You don't see they don't form ion because they don't react. This is a conceptual question you expect to see in the quiz. Main group element has an outer electron configuration of Ns2 and P4, where N stands for the principal energy level. It could be 2, 2, it could be 3, 3, it could be 4, 4, but the most important thing is the superscript, the 2 and the 4. You add the 2 should give you the group number for which this electron configuration represents. The question is most likely form what charge? This is group 6, and it will form a charge of -2. So if I see here, the charge will be formed is -2. This is group 6A. So it's gonna be B. So is Ns2 and P4. This is 6A with a charge of let's say charge here. This is -2. We have N S2 NP3. This is 5A. It's going to form a charge of -3. If it is NS2 NP6, this will be group 8A 0. There is no time for group 8. NS2 NP5. This is 7A. We form a charge of -1. You should be well rounded in predicting the charge formed by a given electronic configuration such as the one we have been given here. So that's enough for section 9.5. Please go back, read the section, make your own notes, use end of chapter problems to answer the question on the using the quantum mechanical model to explain the trend in chemical reactivity for main group element. You should know what isoelectronic means. You should be able to write the electron configuration for ions, which we covered earlier on, for cation, for anion. Let's move on to section 9.6, which is the last part I want to cover in this part P. Trend in atomic radius. You know what the radius is, the distance from the center. This is an atom. This represents the radius using R. Okay, there is a trend on the periodic table. First, let's see, what do we, or how do we define the radius? There is the van der Waals radius, there is the covalent radius, and then there is the atomic radius, is the average radius of an atom based on measuring the large number of elements and the compound. You look at this, let me just blow up this so that you can differentiate or look at the difference between the two types of radius. Bounding radius, this is the bounding radius, and there is the van der Waals. You see the van der Waals covalent radius for me, covalent radius sharing, and then van der Waals for solids. The trend we will look at is for main group, and you know main group on the periodic table, these are the first two columns and the last 6 columns. You'll be given an exam, I'll give you an exam. The periodic tables will not be colored as the one you see on the screen, but these are the A's. If you look at 1A, 2A, 3A, 4A, 5A, according to American convention, all the way to 8A, these are main group elements. The trend we look at for those elements, the main group, we're gonna have the group 1A, 2A, 3A. Generally, as you move across the periodic table, there is a trend. As you move down the periodic table, there is a trend, and you should commit this to your memory. You should be able to explain why. You look on this diagram, this is helium, group 8, neon, group 8, argon, group 8, krypton, xenon. They have the lowest. When you move from sodium, lithium, sodium, potassium, rubidium, and cesium, the atomic radius increase. So here, this is what's happening. You should visualize this for donor group. Let's say atomic radius. It decreases as you go from left to right, and it increases as you go down a group. And the reason being, as you add electron to the same shell as you move across, the effective nuclear charge increase, which shrinks the atoms. In other words, moving across. Let's see across. This is lithium. I should use this. lithium here, Li, and then there is one electron for lithium, which is across. And then for fluorine, with 9 electrons, I would need 7 here. 1, 2, 3, 4, 5, 6, 7. We are adding electron with the same shell, adding electron with the same valence shell. So here we are adding, this is fluorine, number 9, adding electrons. Okay. Same shell actually make the atom to shine. So if I go across, I'll say this, as we add to the same shell, it's decreasing, 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 because the nuclear charge keep on increasing. So it's decreasing across because of adding the same. Now moving down is you are adding the principal energy. For this effective nuclear charge, which is pulling the electrons towards the nucleus, will increase valence shell held together. This explains the trend going across. But going down a group or going up the group, the principal energy increase. In other words, this is shell number 1. We have 2 shells. We have 3 shells. Right? If I have 4 shells, it keeps on increasing. So this increase down the group. For a particular group, the outermost energy level keep on increasing, making the trend on atomic radius to increase. So that's one of the trend on the periodic table for main group element. You should be able to state, you should be able to explain as you go across, atomic radius decreases. As you go down a group, the atomic radius increases. Or in exam, in a quiz, you may be given a series of elements and you are asked to rank them according to atomic radius or according to decrease in atomic radius, decrease in atomic radius is the same thing, or which one of the following element has the least atomic radius and so forth. You should be well-rounded in all those kind of questions so that you answer. But remember the general trend on atomic radius. The picture here demonstrate or illustrate the trend as you go across the periodic table, it decreases. On the transition metals, the decrease is not as high as main group element, and as you go down a group, it increases. So as you go up, it decreases. As you go from right to left, it increases. You may not know the exact atomic radius for silicon or phosphorus, but based on the position on the periodic table, you should be able to tell that silicon has, smaller atomic radius compared to phosphorus, or xenon should have the largest atomic radius compared to any group 8 elements. That's the trend on atomic radius. Atomic radius. Effective nuclear charge, this is also one of the trend you need to know. First, what is effective nuclear charge? Effective nuclear charge, abbreviated C subscript EFF. This is the notation for effective nuclear charge. It's defined as the net positive charge that is attracting a particular electron. In this case, we are referring to electron in the outermost shell. Let's say chlorine, for example, which is number 17. Chlorine number 17. This is the innermost shell with 2 electrons. This has 8 electrons, 6, 8, so 10, and then 5. So 1, 2, 3, 4, 5. Let's see. Do we have 17? 1, 2, so 2, 3, 4, 5, 6, 7, 8, and 10, and 12, 13. So this is 5, 17. We have 17 electrons for chlorine. And the C effective in this case is what is the net charge being felt by this electron. To calculate that, C effective for particular electron is given by Z minus S, where this is the number of valence. This is the number of valence electrons. This is the valence electrons. This is valence electrons, and this is total number of valence electrons. You may not, or you will not be asked to calculate the C effective, but it's good to know this is an S, which is the number of valence electrons. So what we want to do for chlorine, this will be 17 minus 5. So we have core electron, which is 10 minus 5. It will give you the C effective of positive 1. If you plug in the number of total valence electron minus the shielding. So effective nuclear charge for many properties depend on the attraction between the nucleus. See this, the nucleus and the outermost 3s electron, valence electron for sodium. We have 11 protons. Then 10 core electron, we subtract, we have positive 1. So for chlorine, we have 17 minus core, which is 10. So if I was to do for chlorine, this will be 17 minus 10. 17 minus core electron 1, 2, 3, 2, 3, 4, 5, 6, 7, 8, 9, 10. Minus 10, this is 7. For lithium, if you look at the sodium, we have 11 minus the core electron, which is in this case 10, there is a positive 1. So electrons are both attracted to the nucleus and they repel one another. The forces on the electron depend on so many factors. So this is C effective, and the trend on the periodic table, you see it's increasing from left to right on the periodic table. C effective, it is a trend which increases across the periodic table, lithium all the way to argon. It increases slightly down the periodic table, which that is what I want you to remember. The trend on so far, trend on atomic radius, you should know the trend on what? Effective nuclear charge increases across the periodic table, slightly increases down the group. Having gone through that, the greatest effective nuclear charge in many electron atoms is experienced by what the one which is closest. Of course, it's this one is A, the closest to the nucleus. This is A 2s because it is closer to the nucleus. This one will be the least, the one with the least nuclear charge experience 6s. In a similar way, I think with a 50 electrons, electron in dash subshell experience the lowest effective nuclear charge. Which one? The least. That means the one with the most oxidized and value the outermost. So S, this will be D5 D because it's in the outermost. How do we know that? You know, this is 1s2 or 2s2, or we have that. How do we know that? This from the electron configuration. 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 3d, 4d10, 4f14, let's be some coin, 5s2, 5p6, 5d10, 5f14, 6s2, 6p6, 6b10, 6f14, so we close this one, 1, 2, 2, 3, 3. So this one, among all these we have here, the last one is right here. This one is right here. So it's going to be the list. If you look at 5s2, it's just right there. 1s is right there. 3d is somewhere there, and 5b, 3b is somewhere there. So this one is the least, is the most outside, and it experiences the least effective nuclear charge, putting it towards the nucleus. That's how you answer the question. If I go back to this, in case you're wondering, how did I come up with 2s? It is closer to the nucleus, 2s. 3s is away. Remember when we write the electron configuration? So this one will be for that 2s for that. Shielding revisited. We talked about the shielding before, which I don't want to get in details into how the outermost electron in an atom is shielded by the core electron. Remember how we calculate the effective nuclear charge for lithium with 3 electrons, total number of electrons minus the core, positive 1. This experience the least because of the shielding by the core electron. Atomic size of atoms and ions. There's a difference between the trend on the atomic radius of neutral atoms and ionic radius of ions based on the nucleus. I know we talked about the atomic radius, the trend is decreasing and increasing. Which part this calls for understanding the trend on the periodic table with respect to the atomic radius. Which part of the electron or periodic table, top or bottom, left to right, has the element with the largest atom? Should be here. If I go down, this will be getting large and large and large and large, and then it's getting small, small, small as you go here. So we want to see the periodic table as the element with the largest atom. It is bottom, so it's gonna be bottom and left. So it's bottom left. This is the periodic table. This is the periodic table. It's gonna be bottom left is when we have the largest atomic radius. For the sizes, it doesn't follow the same pattern. If an element loses one of its valence electron or one, its ion becomes small. Cations are smaller in size compared to their parent atoms. Look at the sodium and the sodium ion. Look at the potassium and the potassium ion, rubidium and the rubidium. Ions are always, or rather cations, are smaller in size than just the neutral atom. The reason for this is that ionic size depend on the nuclear charge, but as the nuclear charge increases, the force of attraction between the electrons remaining and the protons in the nucleus increase, therefore shrinking the atom. The number of electrons also decrease, which they reside on the orbitals on these cations. For anion, it's the opposite. Anions which are negatively charged are always larger compared to the parent atoms. For oxygen, for fluorine, all these two-colored anions which are negatively charged have larger atomic radius because when they gain electron or electrons, their radius keeps on increasing. You got to be careful with the cations and anions. Cations are smaller in size compared to their parent atom with neutral form, and the anions which are negatively charged are always larger in size compared to parent atom. Reason being, in cations, they are small because the outermost electron is removed and repulsion between electrons are reduced, whereas for anions, which are larger, electrons are added and the repulsion between electrons are increased. No one will ask you about the actual numbers, but you need to know the trend. I think I've explained the trend on atomic radius. I will come back again in part C. Please attempt end of chapter problems. Look at the self-check quiz. Go to Alex, complete module 9 for chapter 9. See you soon in part C. Thank you.